It's the wild when you think about how much data AI can handle these days. I mean, it's really incredible, right? Like mountains of data, no problem. But then throw some complex scientific research at it. And suddenly it's like AI's hit a brick wall. All that jargon, symbols, it's just not easy for it to digest. So that's what we're diving into today. This essay we found, figuring out if we can actually make AI think about science, more efficiently. Like, what if we could translate all those dense research papers into something AI gets instantly? And to help us unpack all this, we've got an expert who speaks both AI and, actual science. So this essay keeps mentioning this bottleneck with AI and scientific terms. What's the issue there?
Well, it all comes down to how we represent scientific information. It's like, imagine trying to find a book in a library, but instead of a simple code, you have to use the entire title, the author's birthday, and who knows what else.
Okay, yeah, that's going to get messy, Sass. So how does this essay suggest we fix that?
It's a pretty fascinating system they propose. They call it compressed symbolic representation. Basically, it's like giving every single scientific term its own unique code. Think like a Dewey Decimal System, but for science.
So instead of photosynthesis, it's like P17382 or something.
Exactly. And because computers think best in numbers, they even turn those keys into binary and hexadecimal codes, all those ones and zeros.
Right. The language of computers. But then how do we understand what's going on? I don't speak binary.
See, that's the clever part. They use these symbols, like flags almost, to show us where the codes are. So you might see AP17382, and you know right away, okay, that's a code, even if I don't get the numbers themselves.
So it's like giving AI its own efficient language, but with, like, subtitles for us. I like it.
Yeah.
But how does this actually work in practice?
The essay gives a really good example using the term a value from chemistry. It gets assigned a key, binary, the whole works.
So the AI can use what makes sense for it, but then translate it back when it needs to show its work, basically.
Exactly. It's all about finding that balance between efficiency for the AI and transparency for us.
Now that is elegant. I'm impressed. And I'm guessing it doesn't even stop there, right? What about all those symbols and equations scientists love?
You're right. Those are a whole other challenge. Like, it's one thing for an AI to recognize something like, say, a Greek letter, but understanding what it actually means, let alone a whole formula, that's another thing entirely.
It's like teaching a computer the alphabet and then expecting it to, I don't know, write poetry.
And the essay actually tries to tackle that. They propose adding even more fields to this system. So there's symbol for those Greek letters and all, then char code, which can represent any symbol, even if you can't display it directly.
So no matter what you're using to look at this, you're not missing any crucial info. That's important, for sure.
Absolutely. And then, and this is cool, there's even a field for LaTeX the code used to make all those nice-looking equations you see in research papers.
So whether you're human or AI, everyone's on the same page. I love how thorough this system is. This feels like way more than just a neat trick, though, right? This is about AI really being able to process science. Let's unpack why this matters after a quick break. Okay, so we're back. Still deep in the world of AI and how we can, potentially get it to think more like a scientist, which is pretty wild. But before the break, we were getting into this system that's kind of like a universal translator for sciencey stuff. Symbols, equations, you name it. I gotta ask, why should anyone care about this if they're not, like, doing research or something? What's the big deal here?
That's the really exciting part. This idea, it has implications way beyond just science. Just imagine AI that can understand any kind of technical language with that same speed and efficiency.
Okay, so we're talking, like, legal documents, financial stuff.
Exactly. Even medical records. Anything with its own kind of jargon, It could completely change how we deal with all that complex information.
That's pretty amazing. But it also makes me think about that whole black box problem with AI. If it's thinking in its own little language, how do we know it's not going off the rails somewhere, making decisions we don't get?
Well, that's the beauty of this system. Remember those breadcrumbs. They're not just there for looks. They let us peek into how the AI is thinking, what concepts it's using, how it's connecting things.
More transparency with AI is always a good thing. But could we even take it a step further? Could AI actually explain its findings to us in a way that, makes sense?
Absolutely. Imagine getting an explanation from AI that actually sounds, well, normal. Clear summaries, even for super complicated stuff.
Now, that would be a game changer for sure. No more spending hours decoding jargon just to figure out what it found.
Exactly. Think about the possibilities in research. Imagine AI helping write papers, creating reports with all the equations perfectly formatted. And the best part is, The logic behind it all would be clear and understandable to the humans.
It's like researchers could suddenly focus on the big questions and let AI handle all the tedious stuff.
It's not even just saving time, though, right? It's about speeding up discovery itself.
Right.
When AI can handle scientific knowledge that much faster, it frees us up to, well, to actually push the boundaries of what we know.
We've gone from AI struggling with jargon to, like, AI potentially changing how we do science. It's mind-blowing.
And it all comes back to this one key thing,
Mm.
bridging that gap between how humans think and how AI thinks. This essay, it really makes you realize how crucial that is as we enter this new age of, really powerful AI.
It's amazing to me how we started with AI, like choking on scientific lingo, and now we're talking about it changing the game for research entirely. This whole conversation has been eye-opening.
And that's what makes this essay so interesting. It's not just about the technical stuff, it's about the potential, the possibilities. One thing that really stuck with me was this whole idea of the system being scalable.
Scalable, so like it can handle more information.
But it's more than that. It
Yeah.
means as we make new discoveries, the system can actually grow and adapt along with us.
Okay, so it's learning as we do.
Yeah. Imagine AI not just understanding our scientific language, but actually evolving alongside it, like helping us shape our understanding of these new discoveries.
Wow. So AI is not just a tool, it's almost like a collaborator at that point.
Exactly. It gets a seat at the table of scientific discovery?
That is pretty incredible when you think about it. Makes you wonder what happens when AI starts thinking about science in ways that, well, that we don't even fully get. What could we unlock then?
That's the big question, isn't it? And this essay, it doesn't try to give all the answers, but it does make one thing really clear. As AI gets more and more powerful, the real challenge, the really crucial thing, is figuring out how to bridge that gap. How to bridge that gap between how we think and how AI thinks.
Finding a common language, even if it's not, a language in the traditional sense.
Exactly. It's about transparency, making sure AI's thought process is something we can at least try to grasp, even as it goes into these areas that maybe we don't fully understand ourselves.
Well, that is a lot to think about. This deep dive has been incredible, exploring the future of AI, not just analyzing data, but really truly understanding science and maybe even shaping how we do it. So, on that note, we'll wrap things up here. We hope this has given you a new perspective on the amazing things AI might be able to do in the world of science. Until next time, keep those brains buzzing. Okay, so have you ever been reading an article, like about some new scientific discovery, and all of a sudden, bam, it's like you're drowning in jargon?
Oh, absolutely. It's easy to feel like you need a scientific dictionary just to get through a single paragraph sometime.
Right. And it's a shame because science is fascinating, but those technical terms, they could be a real barrier.
For sure.
Well, what if I told you there's a system out there, a kind of a secret decoder ring for scientific lingo?
Oh, intrigue me.
Today, we're diving deep into this thing called functional categories. And honestly, it sounds way more boring than it actually is.
Okay, I'm listening.
Basically, imagine instead of just defining terms in isolation, we organize them by what they do, their function in the grand scheme of science.
Oh, interesting. So, like, instead of just knowing the definition of, say, photosynthesis, we understand its role as a process.
You got it.
Yes.
It's not just what something is, it's what it does. And that little shift, well, it can completely change how you see scientific concepts.
I can see how that would be helpful, breaking things down by their function. I like it. So, how does this whole system work?
Well, our sources dive into several key categories, but a good place to start is with, well, concepts.
Makes sense. Concepts, kind of the building blocks of any scientific field. So, what are we talking about here?
Right. And this is where it gets cool. We're not just talking about like dictionary definitions, we're talking about the big ideas, but also how wildly they can range.
Okay, give me an example.
So you could have a concept as mind bending as like quantum entanglement, right?
Whoa, yeah, getting pretty out there.
But then on the flip side, you have a concept like energy conservation, which is, super fundamental, but still a concept under this system.
Okay, so a pretty broad spectrum. I'm seeing how this is more than just memorizing definitions.
Exactly. And it gets even better. Our sources actually break down concepts even further into different types.
Okay, like subcategories of concepts.
Precisely. You've got theoretical concepts, which are often based on, well, theories and abstract ideas. Stuff like electronegativity, or the whole concept of activation energy in chemistry.
Right, so those are more about the models and explanations we use.
And then you have mathematical concepts, like those tricky wave functions. which, let's face it, are basically using math to describe how things work.
Math, always got to bring the math in.
It's unavoidable. But you see what I mean? This system is showing us that science isn't just about knowing a bunch of facts.
It's about understanding different ways of thinking.
Exactly.
Yeah.
Different ways scientists approach problems, make predictions, all that good stuff. I love it.
Okay, so we've got theoretical concepts, we've got mathematical concepts. What else?
Well, according to this, there are also things like chemical principles, like, how redox reactions work.
Okay, so specific rules within chemistry.
And then you've got physical constants like the speed of light, which is always fun to think about.
Right, those unchanging values that pop up everywhere.
But this is where it gets really wild. Ready for this?
Hit me.
Our sources say that even philosophical concepts can be considered a type of concept within science. Things like causality.
Wait, hold on. Philosophical concepts, like what we think about, like cause and effect, that kind of thing.
That's what it seems like. Or like Occam's razor, that whole idea that the simplest explanation is usually the best.
Okay, now that is interesting. So we're not just talking about the what of science, but also the how and the why behind how we do science.
I know, right? It's like this system is pulling back the curtain on the whole scientific process. It's not just about the findings, it's about the framework we use to understand the world.
I'm liking this functional categories thing more and more. So we've tackled concepts. Where do we go from here?
Well, if concepts are the building blocks, then next we got to talk about the blueprints for how things happen.
Processes.
All right, let's talk processes.
Okay, so we've covered the what with concepts, and now it's time to dive into the how. Ah, yes, because what's science without a little action?
Right, and this is where things get really fun, like stepping into a scientific toy store.
You know, I love a good gadget. What are we talking about here?
Our sources call this category equipment tools, and it covers everything scientists use to explore those concepts and processes we were just talking about.
All right, so give me some examples. What kind of cool tools are we talking about?
Well, you've got everything from like the incredibly complex, the mass spectrometer.
Mass spectrometer, that sounds intense.
Right, it's this amazing instrument that can basically analyze a sample and tell you exactly what it's made of, down to the individual atoms.
Wow, that's some serious detective work. So how does it even work?
Honestly, I'm not entirely sure I understand it myself. Something about measuring the mass-to-charge ratio of ions.
Okay, well, maybe we can save the inner workings for another deep dive. But the idea of being able to identify something completely unknown at the atomic level, that's pretty amazing.
It really is. And then on the, well, less complex end of the spectrum, you have things like the calorimeter.
Calorimeter, that sounds a little more my speed.
Right. It's used to measure heat transfer during like a chemical reaction.
Yeah.
So you mix two things together, and the calorimeter tells you how much heat was released or absorbed.
So it's like a tiny little thermometer for chemical reactions.
Exactly. And it's a great example of how even a seemingly simple tool can be incredibly useful in science.
Absolutely. And speaking of tools, our sources also mention computational tools as a subcategory here.
Oh, right. Because in this day and age, you can't talk about scientific tools without mentioning computers.
Exactly. We're talking simulations, data analysis, modeling. It's all become such an integral part of the scientific process.
It's amazing to think about how the tools themselves are evolving alongside our understanding of the world.
It really is. It makes you wonder what incredible tools scientists will come up with next.
Okay, so we've got concepts, the building blocks, we've got processes, the actions, and we've got equipment tools, the instruments. What else is there?
Well, next up, we need to talk about the consequences, the outcomes, the ripples that occur as a result of all those things. We need to talk about effects.
Effects. So if we think about processes as the verbs of science, are effects
Yeah.
like the direct objects?
I like that analogy. Yes, effects are all about what happens as a result of a particular action or interaction.
Okay, so give me some examples. What kind of effects are we talking about here?
Well, our sources mention the classic photoelectric effect, which was, kind of a big deal back in the day because it demonstrated the particle-like nature of light.
Oh, right, that whole wave-particle duality thing. It always messed with me a little bit back in school.
Yeah, it's a head scratcher for sure, but it's also what makes things like lasers possible, so that's pretty cool.
Very cool. What else?
Let's see, we've also got the Doppler effect, which explains why the pitch of a siren changes as it moves towards or away from us.
Oh, right. The sound waves get compressed as the siren approaches, making the pitch higher. It's something we experience all the time, but I bet most people don't even realize there's a scientific explanation for it.
Exactly, and it's not just about sirens either. The Doppler effect is used in all sorts of applications, from astronomy to, like, the radar guns police officers use.
It's amazing how these effects, these seemingly simple phenomena, can have such far reaching implications. It really makes you appreciate the interconnectedness of everything.
Precisely. And just like with our previous categories, effects can be further classified to help us make sense of them.
Okay, I'm intrigued. Break it down for me.
Well, according to this, we've got optical effects, which obviously deal with light, electrical effects, which are all about charges and currents, magnetic effects, magnets and their fields.
Right, and I'm guessing there are chemical effects too?
You know it. Chemical effects are all about the changes that happen as a result of chemical reactions.
So we're basically talking about all the different ways things can impact each other, all neatly organized into these different types of effects.
Exactly. It's all about understanding cause and effect, which is really what science is all about when you think about it.
This is blowing my mind. It's like we're taking all this complex scientific knowledge and organizing it in a way that actually makes sense. Okay, so what other categories are we exploring in our functional categories adventure?
Ready to tackle another category.
Hit me with it. We've covered so much ground already, I feel like we can take on anything.
All right, let's talk about the bedrock of science, theories, laws.
Ah, the heavy hitters. We're talking Newton's laws of motion, the theory of relativity, stuff that makes you realize just how much we've figured out about the universe.
Exactly. These are those grand unifying principles that have stood the test of time. They're not just guesses, they're the foundation for how we understand everything else.
Right, like they provide the framework for all the other scientific knowledge we've been talking about. And our sources say this category isn't just limited to like physics, right?
Oh, not at all. We've got physical laws like the ones you mentioned, but there are also chemical laws, things like the law of conservation of mass.
Right, right. The one that says matter can't be created or destroyed. It's like
Yeah.
a fundamental rule of the universe.
Exactly. And it highlights how these laws apply everywhere, from the tiniest atom to the largest galaxy.
It's incredible, isn't it? Makes you realize how interconnected everything is. But what about those like mathematical theorems that seem to underpin so much of science? Do they fit into this category too?
They do. Our sources actually list mathematical theorems as a distinct type of theory or law. Things like Pythagoras' theorem,
Oh, right. The one about the sides of a right triangle. I vaguely remember that from school.
or the whole concept of limits in calculus, which helps us understand infinite series and things like that.
It's amazing how these mathematical tools, often developed in the abstract, can have such profound implications for understanding the real world.
It really speaks to the power of mathematics as a language for describing the universe. It's not just some separate field, it's woven into the very fabric of how we understand the world around us.
This is making me want to go back and retake all those math classes I barely scraped by in.
Maybe we can do a deep dive on math sometime, but for now, we've still got a few more categories to explore.
All right, what's next?
Let's zoom in a bit from those big picture theories, laws, and talk about properties.
Properties. So we're talking about the specific characteristics that describe matter.
Exactly. Things like viscosity, which is how easily a fluid flows honey versus water.
Oh, okay, I see. Or like density. That always trips people up, the whole idea of a bowling ball and a beach ball having the same volume but drastically different densities.
And who could forget about solubility, which basically determines whether or not something will dissolve in a liquid.
Which, as we all know, is crucial information when you're trying to make a decent cup of coffee.
Exactly. It all comes back to coffee eventually. But seriously, these properties are all around us. And just like our other categories, they can be further categorized to make them easier to understand.
All right, lay it on me. What kind of properties are we talking about?
Well, you've got your physical properties like boiling point, color, whether something's magnetic or not. These are all things you can observe without, like, changing the chemical composition of a substance.
Yeah.
And then you've got your chemical properties.
Which describe how a substance is going to react in a chemical reaction.
Exactly. Things like whether something's flammable or how acidic it is or how easily it reacts with other substances.
It's like having a cheat sheet for understanding how matter behaves under different conditions.
Precisely.
This functional category system is amazing. It's like someone finally organized all of scientific knowledge in a way that actually makes sense. We've covered concepts, processes, equipment tools, effects, theories, laws, and properties. Is there anything we missed?
Well, our sources do mention one final category, other.
Other, it sounds a little ambiguous. What ends up in the other category?
It's a testament to the fact that no system is perfect and that science is constantly evolving. This is where you find things like interdisciplinary fields, those areas where different scientific disciplines overlap.
So like bioinformatics or nanotechnology, fields that combine elements of like biology, computer science, engineering all in one.
Exactly. And then you've got emerging concepts of the cutting edge of science that's still being developed and debated.
So we're talking about things like quantum computing or CRISPR technology, the stuff that sounds like it's straight out of science fiction.
Precisely. The other category is where the really exciting, unpredictable stuff happens. It's the wild west of scientific discovery.
I love it. This whole deep dive has been incredible. But I think we need a little recap because we've covered a lot of ground today.
Absolutely. I think the key takeaway here is that scientific language doesn't have to be a barrier to understanding. This functional category system gives us a framework, a way to organize all those complex terms and concepts. It's like having a mental map to navigate the world of science.
I couldn't have said it better myself.
Right.
So the next time you're reading an article or watching a documentary and you encounter a scientific term that sounds like gibberish, don't panic. Think about the functional category system. Ask yourself, is it a concept, a process, a tool, an effect, a theory, law, a property?
Chances are, just by categorizing it in your head, you'll start to understand it better.
It's all about breaking down those mental barriers to knowledge and realizing that science is for everyone. And if you ever need a guide on your journey into the fascinating world of science, you know where to find us. All right, everybody, get ready because today we are diving deep into something really cool from your notes. It's this idea of key-based dimensional analysis. And honestly, it sounds like it could be a real game changer.
Well, I definitely think it has that potential, yeah.
The way I see it, like we're talking about bringing some desperately needed clarity and consistency to, well, how we even talk about science.
Yeah, no, I completely agree. The way we do things now, with all its ambiguity and inconsistencies, it's a mess. It's like trying to navigate through a maze blindfolded.
Ugh, tell me about it. Like,
Yeah.
ever spent way too long staring at an equation, wondering if that P is pressure or momentum?
Happens all the time, right?
But with this new system, every single term gets its own unique ID. It's like a digital fingerprint for scientific concepts, so no more mix-ups.
Right. It's like having that universal translator we've always dreamed of, but for scientific data.
And that's huge. Just think about it. What if every single database, every research paper, everything used this system?
It would be revolutionary. It would fundamentally change how we access, understand, you name it, when it comes to scientific knowledge.
Okay, so before we get too far ahead of ourselves, let's break down an example. In your notes, you mentioned the momentum equation, something I think most of us vaguely remember from, what, high school physics?
Right, and I'm sure everyone remembers the classic PMV, which, let's be honest, isn't the most descriptive thing in the world.
You're telling me.
Mm.
But in this new system, instead of those letters, we'd have these specific unique keys for each term.
Precisely. So instead of P for momentum, you might have, say, M04007. Mass could be M04002, velocity M04001. You get the idea.
No more squinting at equations trying to remember what's what. And here's where it gets really cool. Each of those keys is linked to a database entry. So you've got the term's definition, its units, even historical context, all a click away.
It's like having instant access to an entire encyclopedia of scientific knowledge just waiting there, right beneath the surface of every equation.
Imagine that.
Well,
The entire history of scientific thought, all linked and interconnected.
and because everything is clearly defined, the system can actually check if your equations make sense.
Wait, hold it. Back up a sec. You're talking about dimensional consistency, right?
Hmm.
For those of us who haven't looked at a physics textbook in a hot minute, what does that even mean?
Good point. Basically, it's making sure you're not mixing apples and oranges. Like, you can't add seconds and meters, right? They're different units.
Makes sense.
This system can spot those kinds of mismatches in even the most complicated equations.
Which is incredible when you think about it, like a built-in error detector for science.
Yeah.
But how does it actually work? You mentioned something about a JSON structure, and full disclosure, my eyes kind of glazed over at that part.
Don't worry, it's actually a lot simpler than it sounds. Think of it like a super organized index card system for scientific terms, but digital. Each card has all the key info.
Right.
The term's name, the symbol we normally use for it, a clear definition, what units it uses, and of course its unique key.
So we're taking all of scientific knowledge and putting it on these digital index cards.
Essentially, yes.
And because it's all structured data, computers can actually understand and use it.
Exactly. And that opens up so many possibilities for automation and analysis, which, we'll get into more a little later.
So we've taken this massive amount of scientific knowledge and we're organizing it, putting it onto these like digital index cards. It's like, what's that saying? Out with the old, in with the new.
It's definitely about more than just organizing what we already know. This is about what we can do with that knowledge with the help of technology.
Right. And that's what makes this whole thing so exciting. Like in your notes, you talked about using software to actually discover new equations. And whoa, my mind kind of short circuited for a minute there.
Yeah.
That's next level stuff.
It's pretty wild when you really think about the possibilities. Imagine feeding all this structured data, all these relationships, into an AI.
It'd be like having an army of superpowered scientists, except, without the risk of a robot uprising.
Well, let's not get ahead of ourselves. The point is, it could analyze connections on a scale we can't even fathom right now. It could be discovering patterns we never even thought to look for, potentially even predicting breakthroughs before we even knew what questions to ask.
Okay, so AI scientists taking over the world aside, let's bring it back down to earth for a minute.
But,
What are some more immediate applications for this?
well, one area that really stands out to me is education. Think about it. How many times did you struggle with some complex equation in school?
Ugh, don't even get me started. I practically lived in the library, drowning in textbooks.
Right. Now imagine, instead of just staring blankly at a page full of Greek letters,
Yeah.
you have this digital textbook built on this key-based system.
Okay, I'm intrigued. Keep going.
You could click on any term that's tripping you up, like say enthalpy in your chemistry equation is making your brain melt. Click it, and boom, you've got a crystal clear definition, maybe even an animation or simulation to really drive the point home.
So, like having a personal tutor built into your textbook, no more late night cram sessions fueled by stale coffee. Sign me up.
Exactly. But this goes way beyond education, too. Think about research itself. Right now, trying to navigate the world of scientific databases, it's like everyone's speaking a different language.
It's true, and it's incredibly frustrating. Every field has its own jargon, its own way of doing things.
And that lack of a common language really holds us back, slows down collaboration, makes it tough to share findings.
Yeah.
It could even mean missing out on huge discoveries.
But with this system, it's like we're creating that universal translator we talked about earlier.
Right. We're on the same page, speaking the same language, regardless of what field we come from.
Imagine the possibilities if we could break down those walls between disciplines.
Precisely. That's where the real magic happens. When we can connect those dots, share those insights, that's when we start seeing breakthroughs in medicine, materials, science, climate change. The sky's the limit.
It's almost overwhelming when you think about it, like the sheer scale of what we could achieve if this thing actually works. But easier said than done, right? Building this kind of universal scientific language. It's a long game, for sure.
Oh, absolutely. It's a massive undertaking, but I don't think it's impossible. Like, we don't have to, do everything all at once.
Right. Rome wasn't built in a day, right?
Exactly. In fact, the notes suggested starting with a smaller goal, like focus on one specific field, maybe chemistry or physics, as a kind of a test case.
A pilot program for science. I like it.
Yeah. And then as you build it out, you get feedback from real scientists working in that field.
So it's constantly evolving, improving based on like real world use.
Exactly. And that's crucial. We don't want to create this rigid system. It needs to be flexible, able to grow and adapt as, our scientific knowledge grows, which actually brings us back to AI.
Because who better to help us wrangle all this complex data than, our trusty AI assistants?
Right. It's like we're talking about building the ultimate research partner.
One that doesn't need coffee breaks or complain about grant proposals.
Exactly. Think about it. AI that can sift through these massive data sets, finding all these hidden connections, maybe even pointing us toward new avenues of research. It's like, what if, instead of just crunching the numbers, AI could help us understand the underlying principles behind those numbers?
It's like giving the scientific method itself an upgrade.
It really is. We're talking about pushing the boundaries of what we thought was possible. But it all comes back to that one crucial element: building that common language, that bridge between how we humans understand the world and how computers process information. And that's what makes this whole key-based system so fascinating. It's not just about, making science neater or more organized.
Right. It's about something much bigger.
It's about laying the foundation for a future where humans and machines work together side by side to unravel the universe's greatest mysteries.
Well, folks, it started as a deep dive into some intriguing notes, has turned into a glimpse into a future that is brimming with possibility. A future where scientific knowledge is more accessible, more interconnected, and dare I say, a little less ambiguous. And who knows what incredible breakthroughs await us just on the other side of that equation. Thanks for joining us, and until next time, keep exploring.